This is the USNSC, and it's about to swallow enough Marine Corps equipment to win a war. But transporting this equipment halfway across the world is a lot more complicated than just throwing a bunch of stuff on a boat and sailing it off. In fact, there are thousands of hidden steps to this process where an error measured in inches could quite literally sink a ship or lose billions of dollars in equipment. And it all starts here at Naval Station San Diego. On this morning, the Marines of Combat Logistics Regiment 1 and Navy Cargo Handling Battalion 1 are moving an entire Marine Brigade's equipment destined for the Middle East. As the first of 742 vehicles lines up on the pier to go up the ramp, the cargo handler stops. Not because something's wrong, but because this specific vehicle, an M1A1 Abrams tank, has to enter the ship first. The reason this tank goes first isn't random. It's because of something called a load plan. A load plan is essentially a massive instruction manual that dictates where every single piece of equipment goes inside the ship, down to the inch. This plan exists because of something even more important called center of gravity. On board a ship like the USNSC, the center of gravity sits about 30 feet above the keel when the ship is empty. That's the point where all of the ship's weight balances. Think of it like the fulcrum on a seesaw. Under normal, empty conditions, this ship has no issues. It sits level. It handles waves fine. It turns normally. But when you start putting 8,000 tons of material and equipment on board, it starts doing crazy things with this number. Load the left side too heavy and the ship lists to port. Load too much weight forward and the bow sits low. Now you're plowing through waves instead of riding over them. Load too much aft and the propellers come out of the water in heavy seas. The load plan prevents all of this by calculating exactly where each vehicle needs to go to keep that center of gravity within 6 inches of optimal. 6 inches on a ship that's 950 feet long. So this Abrams tank rolling up the ramp at exactly 3 miles per hour isn't just going somewhere on the ship. It's going to position Charlie 7 on Deck 3, facing starboard with its turret traversed to 270 degrees. The position matters because the turret weighs 22 tons. Point it forward and you've just moved 22 tons forward. Point it backward and you've moved 22 tons aft. Multiply that by dozens of tanks and suddenly the ship's trim is off by 2 degrees. As the tank driver looks through his periscopes, he can't actually see where he's going. The ramp is at a 12-degree angle and all he sees is steel deck and shadows. So he relies heavily on ground guides, Marines standing outside using hand signals that haven't changed since World War II. Raised fist means stop. Flat palm pushing down means slow. Arms waving means move forward. The driver keeps his turbine engine at exactly 800 RPM. Any higher and the tracks might spin on the anti-skid coating. Any lower and he might not have enough power to climb the ramp. If he stops halfway up, he might not be able to start again. The physics of starting 68 tons from a dead stop on a 12-degree steel incline covered in salt spray and hydraulic fluid means he needs momentum. While this tank climbs, something interesting happens below deck. The ship's ballast system kicks in automatically. See, when 68 tons of tank starts climbing from sea level to Deck 3, the ship's center of gravity shifts upward and aft. Computers detect this instantly and begin pumping seawater between ballast tanks. Right now, 10,000 gallons are moving from forward tanks to aft tanks to compensate. The ship must stay level within half a degree. Any more and the ramp angle changes enough that the next vehicle might bottom out. The tank reaches position Charlie 7 and stops. Immediately, Marines duck under the hull with chains. But not just any chains. These are rated for 15,000 pounds each, and this tank needs 22 of them. This is because in the middle of the Pacific Ocean, this ship might hit 30-foot swells. When the ship drops into a trough, the tank experiences negative G-forces. It literally tries to float off the deck. When the ship rises on a wave, the tank experiences 2 Gs. Suddenly it weighs 136 tons instead of 68. Those chains need to hold it either way. But here's the critical part. Each chain must be attached at an angle between 30 and 60 degrees. The angles matter because at 45 degrees, a chain rated for 15,000 pounds provides maximum holding force. At 30 degrees, it still provides about 7,500 pounds of vertical force. But drop that angle to 20 degrees and suddenly that same chain can only hold 5,100 pounds. At 10 degrees, it's down to 2,600 pounds. Get the angle wrong and when the ship hits its first storm, that tank breaks free and becomes a 68-ton wrecking ball. The Marines use lever binders to tighten these chains. A lever binder is basically a mechanical advantage device that multiplies force by 30. A person pulls with 50 pounds of force and the chain tightens with 1,500 pounds of tension. They tighten until the binder won't move, then back off a quarter turn. They do this because metal expands and contracts with temperature. Tighten a chain in San Diego's 70-degree morning and by afternoon when it's 95 degrees, that chain has expanded enough to snap from overtension. Behind the Abrams, more heavy equipment waits. A 60-ton Kalmar rough terrain container handler moves into position on the pier. This isn't your warehouse forklift. It's a diesel-powered crane on wheels with a telescoping boom that can stack containers 3 high. The operator sits in a cab and tilts back 90 degrees so he can see exactly where the container spreader bar connects to the ISO corner castings. Those castings have to align within a ½ inch or the twist locks won't engage. Miss the alignment and you're trying to lift 40,000 pounds by friction alone. The handler grabs a Quadcon, a quarter-size container packed with spare parts weighing 8,000 pounds. As it lifts, the entire machine tilts forward slightly. The operator watches his load movement indicator, the gauge that shows how close he is to tipping over. At full extension, this handler can only manage 30,000 pounds. Retracted, it can lift 60,000. Get the physics wrong and the whole machine tips forward, launching the container like a catapult. Meanwhile, a 7-ton truck waits for inspection. But before it can roll, Marines are going through a checklist that seems obsessive until you understand the stakes. Fuel level must be at 1/4 tank since an empty tank creates vapor and that's more dangerous than liquid fuel. However, they can't load the tank full because fuel expands with heat. A full tank in San Diego becomes an overflowing tank in the tropics. Plus, fuel weighs 6.7 pounds per gallon. This truck's 50-gallon tank, if full, adds 335 pounds. Multiply that variance across 742 vehicles, and you've thrown off the load plan by 93 tons. In addition to the fuel tank prep, Marines disconnect the battery entirely. Not just switched off, physically disconnected and the terminals wrapped in tape. Even disconnected, a battery loses 2% of its charge per week through internal resistance. But connected, even with everything off, modern vehicles have parasitic draws, computers, clocks, alarms that drain a battery completely in weeks. After 3 months at sea, that battery isn't just dead, it's sulfated. The lead plates develop crystals that prevent the battery from ever holding a charge again. A $200 battery becomes trash. Meanwhile, sensitive equipment comes off entirely. A $50,000 SyncGARS radio system gets removed, wrapped in vapor barrier bags with desiccant packs and stored in climate-controlled containers. This is because salt air is basically poison to electronics. It creeps through the tiniest gaps and corrodes circuit boards into green fuzz. One drop of condensation inside a thermal sight and fungus starts growing on the germanium lens. That's now a $20,000 replacement and a gunner without a sight. Special vehicles need special handling. A Humvee with a tow missile system rolls up next. The launcher adds 6 feet of height and 4,000 pounds of weight, all of it high up. This completely changes the vehicle's center of gravity. When it climbs the ramp, the ground guide watches for any lean. Too much angle and this top-heavy configuration could tip. They position this vehicle on Deck 2 where the overhead clearance is 14 feet, just enough for the 12-foot total height plus the chain tension that will pull it down. Light armored vehicles present their own challenges. These 8-wheeled amphibious vehicles weigh 14 tons, but they're designed to float, which means their center of gravity is intentionally high. On the ramp, they're unstable. The driver can't see anything through his vision blocks except steel and shadows. The ground guide has to position himself where the driver can see his signals through a vision block the size of a paperback book. The really heavy stuff requires the ship's own cranes you see here. The USNSC has two 55-ton pedestal cranes that can work together for 110-ton lifts. When an M88 Hercules recovery vehicle needs loading, that's 70 tons of armored maintenance vehicle. Both cranes work in tandem. The operators can't see each other, so a single loadmaster coordinates over radio. Take weight on crane 1, neutral on crane 2. Hoist together on my mark. Any miscommunication and one crane takes all the load, potentially snapping cables rated for 150,000 pounds. This loading process continues for 2 weeks. Every vehicle goes through the same preparation, the same positioning, the same chain-down procedure. By day 3, ammunition containers start arriving. These really can't go just anywhere. Navy regulations require ammunition be separated from fuel by at least one deck. White phosphorus rounds need special ventilation zones. High explosives go deep in the ship where the hull is thickest. If something does go wrong, you want maximum steel between the explosion and the ocean. But once the vehicles and equipment are safely secure in the belly of the ship, a different kind of enemy takes over. The USNSC clears San Diego Bay. 742 vehicles begin their 90-day journey into degradation. The first enemy is the temperature cycling. In the tropics, the cargo decks can hit 130 degrees during the day, then drop to 50 degrees at night. This 80-degree swing happens every single day. Metal expands and contracts. Rubber seals compress and stretch. The chains holding vehicles develop different tensions. A chain tightened to 5,000 pounds in San Diego might carry 7,000 pounds after thermal contraction, or go completely slack after it expands. Salt air infiltrates everything. Ships aren't submarines. They're not sealed. Salt air enters through ventilation systems, door seals, and hatches. It forms crystals on every exposed metal surface. Aluminum corrodes into white powder. Steel develops orange rust. Brake rotors develop a rust film that actually bonds with the brake pads. After 90 days, those brake pads are effectively welded together. Then there's condensation. Warm, humid air hits cold steel bulkheads and water literally rains inside the cargo holds. This water pools on vehicle hoods, runs down windshields, seeps into fuel tanks through breather tubes. Diesel fuel and water don't mix. The water sinks to the bottom where it waits to destroy injection pumps. The fuel itself stratifies into layers. Heavy molecules sink, light molecules rise. The biocide that prevents algae growth settles at the bottom. The lubricity additives that protect injection pumps float to the top. What went in as fresh treated fuel comes out as 3 distinct layers of progressively worse quality gunk. Batteries undergo their own issues. Even disconnected, the chemical reaction inside continues slowly. A battery that could deliver 800 cold cranking amps in San Diego might manage 200 after 3 months. Some batteries swell from the heat, others crack from vibration. The worst ones leak acid that eats through battery boxes. After weeks to months at sea, depending on the mission, the Marines and sailors are going to wake up to the world's worst surprise party when they pull into Saudi Arabia to offload. And unlike onloading, it's not simply reversing the order, it's a completely different process. The USNSC arrives at port in Saudi Arabia. The offloading operation is fundamentally different from loading because vehicles must exit based on mission priority, not load plan sequence. The ship has 3 ramps with different capabilities. Stern ramp rated for 112 tons. Side ramps rated for 40 tons each. The stern ramp can adjust from 0 to 18 degrees depending on tide and pier height. The ship's ballast system actively adjusts during offload. As weight leaves upper decks, ballast water pumps aft to maintain the ramp angle within 1 degree. But before they get vehicles down the ramps, Marines and sailors need to get the chains off, which is now much easier said than done. After 90 days at sea, thermal cycling has changed the chain tension. Chains installed at 5,000 pounds of tension might now hold much more. Marines use a specific sequence. Release upper chains first to prevent vehicles from tipping forward when lower chains release. Each binder requires approximately 15 reverse rotations to fully release. The force required increases from 50 pounds when fresh to 150 pounds when corroded. Once the chains are off, the sailors and Marines use the ship's internal ramp system to move vehicles between decks. These ramps operate at fixed angles, 15 degrees between deck 2 and 3, 12 degrees between deck 1 and 2. The ramps are 20 feet wide with 18 feet of usable width after safety margins. Vehicles must maintain 5 miles per hour minimum speed to prevent stopping mid-ramp where restart is difficult due to the angle. As this is going on, the sailors are setting up the offshore petroleum discharge system to provide fuel transfer capability when no port facilities exist. The ship connects 6-inch flexible hoses that can pump 600 gallons per minute to floating bladders or directly to shore facilities. The system maintains 50 pounds per square inch pressure and includes water separators that remove contamination accumulated during storage. But while today the U.S. military is using a Saudi commercial port for operations without piers, the Navy employs the improved Navy lighterage system. This consists of powered causeway sections that create a 2,100-foot bridge from ship to shore. Each section requires 80 feet by 24 feet, draws 3 feet of water, and connects using automated coupling systems. The causeway can handle waves up to 4 feet and vehicles up to 75 tons. Connection requires precise alignment. The male and female connectors have a 6-inch tolerance. Hydraulic rams rated for 200 tons push sections together while ships maintain position using dynamic positioning systems. When the causeway isn't available, the ship uses side-loadable warping tugs. These vessels have a flat deck that can accept vehicles directly from the ship's ramp. Each tug can carry 180 tons and makes 15-knot transits to shore. Loading requires matching the tug's deck height to the ship's ramp, accomplished through ballasting that adjusts the tug's draft by 4 feet. Container offload uses the ship's 2 pedestal cranes you see here, each rated for 55-ton single or 110 tons tandem. The cranes have a 35-foot reach and use automatic load movement indicators that prevent overextension. Containers transfer using ISO commercial standard twist locks that engage corner castings with a 90-degree rotation. The engagement requires alignment within 0.5 inches horizontally and 2 inches vertically. Anything more than that, and the whole container pile risks tumbling over. But this isn't the only safety concern. Humidity control during offload is critical. Opening cargo doors causes immediate condensation as 95-degree humid outside air meets 75-degree steel bulkheads. The ship runs dehumidifiers rated for 500 pints per day per deck, but once doors open, interior humidity jumps from 45% to 85% within minutes. This condensation creates slip hazards and accelerates corrosion on exposed chains and tie-down points. The ship's cargo offload and discharge system coordinates vehicle movement using 3 separate communication nets: vehicle operators on Channel 1, crane operators on Channel 2, and pier marshalling on Channel 3. Each vehicle gets a discharge number that determines its sequence. Priority 1 vehicles, command and control, exit first regardless of location. Priority 2, combat vehicles, follow. Priority 3, support, exit last. On roll-on, roll-off operations in non-permissive environments, like an active combat zone, the ship can perform an emergency discharge. All 3 ramps lower simultaneously. Vehicles exit at maximum safe speed, 10 miles per hour on ramps, 15 miles per hour on flat decks. The ship's internal traffic control uses light signals: green for proceed, red for stop, amber for caution at deck transitions. Emergency discharge can empty 1 deck in 22 minutes versus 90 minutes for normal operations. The automated cargo documentation system records each vehicle as it crosses the ramp threshold using laser sensors that measure vehicle dimensions and weight distribution. This data feeds to port operations for staging. Any vehicle showing weight imbalance greater than 500 pounds side to side gets flagged for suspension inspection. But getting all these vehicles onto the pier is the easy part. Getting them combat ready in a matter of hours is the real challenge. On the staging area behind the port, all 742 vehicles need resurrection. Marines have 4 hours to turn degraded machinery into combat-ready formations. Battery replacement runs like an assembly line. A Marine can swap a Humvee battery in 3 minutes if the hold down hasn't corroded. If it has, add 10 minutes with penetrating oil and hope. Some battery boxes are so corroded from leaked acid that they crumble when touched. Those vehicles need welding repairs before they can move. Fuel systems need work on half the vehicles. Water in the fuel has reached the injection pumps. Each injector must be cracked open while someone cranks the engine. Diesel sprays everywhere until clean fuel flows. Then retighten and move to the next cylinder. A 6-cylinder engine takes 30 minutes if everything goes right. The worst problems are invisible. Turbochargers that sat still for months have bearings that don't want to spin. When they finally spool up to 100,000 RPM, they sometimes self-destruct, sending metal fragments through the intake. Cylinder walls have developed a glaze from humidity that means engines burn oil from the first start. Mechanics tap brake drums with rubber mallets listening for the ring. A clear ring means healthy metal. A dull thud means heat damage from the lock brakes. Those vehicles get flagged for replacement. The optics that were stored separately need reinstalling, but first they need defogging. 3 months of temperature cycling has pushed humid air past the seals. Thermal sights show condensation on internal lenses. Each one needs disassembly, drying, and purging with nitrogen before remounting. Miss one foggy lens, and that gunner is combat ineffective. As vehicles get repaired, they form into tactical units. First platoon needs 4 Humvees, 2 7-tons, and 1 command vehicle. But 2 Humvees have blown tires, 1 7-ton has transmission problems, and the command vehicle's radios are shot from corrosion. Marines shuffle vehicles between units, borrowing from 2nd platoon to complete 1st platoon's requirements. 4 hours after the first vehicle rolled off, Convoy 1 departs for forward positions. The vehicles don't sound the greatest right now, but they're moving. In 6 hours, the USNSC has disgorged an entire brigade's worth of combat power. The ship raises its ramp and turns for home, leaving 742 vehicles to fight a war they were packed for 3 months ago. Bye for now.